Okay, a demonstration to put these four metrics to the test and see how they act and react to different prevalences of disease and performance of tests. Okay, down here we have our 2x2 table again. At the moment there's just zeros, so it looks a bit ugly, but we're going to fill that in and see how these metrics perform. So in experiment 1 it says set the true positive to 25, false positive to 100, false negative to 25, and true negative to 100. What is the sensitivity and specificity, and what is the prevalence of disease? Okay, let's look. The sensitivity is 50%, the specificity is 50%, and the prevalence of disease is 20%. So we have a total of 250 people here, and 50 of them have the disease, so the prevalence is 20%. Of the 50 people who have the disease, the test is positive in 25 of them, so the sensitivity is 50%. And among the people, the 200 who do not have the disease, the test is negative for 100 of them, so the specificity is 50%. We won't worry about the rest of the table now, we'll look at that later. Okay, now set the false positive to 2000, okay, let's do that, and the true negative to 2000. Okay. So how does this change the sensitivity, specificity, and prevalence? The prevalence is now only 1.23%. We have 4,050 individuals, and 50 of them had the disease. So the prevalence is now lower than before. But the sensitivity and the specificity are the same. Okay, so nothing really changed with respect to sensitivity and specificity. This is a general finding that the sensitivity and specificity don't necessarily depend on the prevalence of disease. This makes it tempting to say, oh well, I have this test which I've evaluated in a group of people over here. Now I can expect the same sensitivity and specificity if I use that test on a group of people over here. But we should be aware that social characteristics may influence the test. The way that we measure disease and not disease may influence. The way that we define what a disease is and what not disease is, what is a case, what is not a case, may be different. So be very cautious with saying that it's easy to generalize your test's sensitivity and specificity just because it doesn't really depend on the prevalence. Okay? In experiment 2, we're going to redo experiment 1. So let me put the numbers back to what they're supposed to look like. So, and now we're going to look at the positive predictive value and the negative predictive value. And we're going to focus mainly on the positive predictive value. Okay. We're back to what it looked like earlier. The prevalence is 20%. The positive predictive value is 20% as well. So what we're saying is, among those who had a positive test, there were 125 in total. There were 25 individuals who actually had the disease. So the positive predictive value was 20%. And if you can look at this at yourself, but the negative predictive value was 80%. Okay. Now we're going to change this to 2000 and this to 2000. What happens now? The prevalence goes down again, just like in experiment 1. But this time, positive predictive value also goes down. Because now I'm saying, among the ones who had a positive test, and in this case we had 2,025 individuals who had a positive test, there were only 25 individuals who actually had the disease. What I'm trying to show here is that prevalence matters for the positive predictive value. So the positive predictive value is going to be dependent on the prevalence of disease in the population. This is something that you need to keep in mind and carefully think about when you see studies reporting positive predictive value. Because if you have a study where you've sampled individuals And if this sample isn't representative of what the population you're trying to generalize looks like, then you might have an issue with the positive predictive value. You might have a higher positive predictive value if your cohort has a higher prevalence of the disease. And this happens sometimes because you oversample the disease, because you have more individuals in the population that don't have the disease than have the disease, and so you oversample people with the disease so that your cohort has more variation or has higher power, and so on. And remember, PPV is very important for the patient, so we want to get this right. Okay. Experiment 3 wants us to set this at 45, 95, 5, and 855. Let's look at the sensitivity and specificity. 90% sensitivity for this test and 90% specificity for this test. So pretty good. But the positive predictive value is quite low. The prevalence is 5% in the population. So now we're going to give you an option. You can either put money into developing your test so that you improve the sensitivity, or you can get money to improve the specificity. And the overall goal is really to improve the positive predictive value. So which one do you prefer? Let's see what happens if you decide that you want to improve the sensitivity. So how would you go and do that? How would you be able to improve the sensitivity? Well, you basically want to move these people up here. You want to make sure that if you have the disease, your test is positive. So you don't want anybody down here. So let's move 4 of these up here. So now we have a very high sensitivity, 98%, but the positive predictive value basically didn't change. You didn't gain anything from doing that. So you've increased sensitivity by 8%, but the positive predictive value hardly changed at all. Okay, so let's set this back. Okay. What if we what if we try to increase specificity instead? So how would we do that? Well, here we have, among the ones who do not have the disease, these people, we want to increase the number of negative tests. So we want to move some of these down here. So let's move 90 of these down here. So we go 5 here, and we go 945 here. We have a much higher specificity of our test now, and the positive predictive value is suddenly 90%. And in general, although you should look at this as a case-by-case basis, when the prevalence of disease is low, then increasing specificity has a greater effect on the positive predictive value than increasing sensitivity. But as I said before, we shouldn't really say that a test is good, bad, or so on based on just looking at these numbers, because it really matters what the test is for and what the intention is. Okay. Our 4th and final experiment, set at the 10, 100, 0, and 9890. Here we have a test which has perfect sensitivity. There were 10 individuals who had the disease, and all of them tested positive. So it's a perfectly sensitive test. The specificity is also very high. You had 9,990 individuals who did not have the disease, and only 100 of them had a positive test. The prevalence of disease is quite low. So it's only 0.1%, which in some cases might actually be high, but in this case, of all the experiments we've looked at so far, this is the lowest prevalence we've seen. Now the positive predictive value is low. Why? Well, despite the fact that this test is really good, you have a high sensitivity and a high specificity, the positive predictive value of the test isn't very good, because the prevalence is very, very low. So among the ones who have a positive test, 110 people, there's only going to be 10 people that actually have the disease. And this raises some dilemmas and ethical concerns, because what if we use this test as a screening tool for this particular disease? Then in this case, you would have told 100 people that they have a disease which they actually don't have, which might have emotional consequences, but also might mean that they get enrolled in the healthcare system unnecessarily. On the other hand, you would also have detected 10 people with disease, and perhaps their prognosis would have improved. Play around with this until you really understand how these numbers and how these metrics are dependent on each other and how you can improve them, and think about what is important in your field of research of these metrics.